Hello students, welcome back. So in the previous video we have seen or we have derived an element stiffness matrix for a bar element. So now in this class we'll move on to numericals on the bars using that element stiffness matrix. So here we have the first problem. The problem says that for a bar shown in figure, find the nodal displacement and stresses. So it's a bar given here, and the load of compressive load of 12 kilonewton is applied at the end of a bar, and you can see here this bar is divided into two elements. It should be divided into two elements in order to solve this numerical. So here till the midspan the distance is 500 mm, and from the midspan to the end it is another 500 mm. So once the question is given like this, the next step, the immediate step we have to start with is the finite element model. So here, first we have to start writing the line diagram or the finite element model. So just write the nodes, location of the nodes. Wherever there is a fixed end, there we need a node. So just write a node, and at the midspan I have created one more node, and wherever there is a load I have created one more node. Join these nodes and first number it 1, 2, 3 and join it 1 to 2. Node 1 to 2 is element 1, node 2 to 3 is element 2, and the compressive load of 12 kilonewton is applied on the node 3. Okay, and node 1 is fixed. You can see here I've just written the fixed lines here. Okay, so next, once you write this diagram, write the boundary conditions. So what are the boundary conditions? The boundary conditions are displacements and the forces. So the first, the displacements and forces. So here the displacements. So displacement I will be representing in Q1, Q2 and Q3. It's in one dimensional bar, so only displacement in the x direction, so only Q1. If it is a two dimensional, at each node it will have Q1 and Q2. Okay, since it's one dimensional, at each node only 1 degree of freedom, that is just Q1. So Q1, Q2 and Q3 for 3 nodes. Similarly, forces. Just forget this part, just write these two things, displacement and forces. Next, for at node 1 F1, at node 2 F2, at node 3 F3. Now try to analyze the displacement at each node. For example, at node 1 displacement can be represented by Q1, but what is the displacement at node 1? See, node 1 is completely fixed. Since node 1 is completely fixed, the displacement at node 1 will be 0. Is this clear? Okay. And node 2 is not fixed. Okay. So there will be some displacement in the node 2. So just I have to find that displacement. That's what it is asking the question, find the nodal displacement. So I have put a question mark, so that it understands that I have to find the displacement at node 2. Similarly, node 3. Node 3 is neither fixed. Okay, so since it is not fixed, the displacement at node 3 also I have to find out. There will be some displacement in node 2 and node 3 because these two nodes are not fixed. Node 1 is fixed, so displacement at node 1 will be equals to 0. Okay. Next, coming to forces. Okay. Node 1 is fixed. Okay. Since node 1 is fixed, there will be a reaction force at the fixed end. Am I right? Okay. So that's why at F1 I am writing it as R1. Okay. So wherever it is fixed, there will be a reaction force. Next, coming to node 2, F2. Is there any F2 force here in the node 2? Nothing, right? No force given here. So it is 0. Coming to node 3, F3. Compressive force of 12 kilonewton is given on node 3. So minus 12 into 10 power 3 Newton is the force acting at node 3. Okay, I think this should be clear. Once you write this, Okay, then the E is given in the question itself. E is equals to 207 GPa, that is 207 at 10 power 3 MPa, and A is equals to 500 mm square. Okay, so once you write this, write the element connectivity table. So element connectivity. Write the element connectivity. Just draw a table. At one side you write the elements. So how many elements are there? 1 and 2. There are only 2 elements here. Okay. Write the connectivity between these elements. So write the connectivity. So first element is connected between the nodes. This is the element and this is the nodes. Okay. So first element is connected between the nodes 1 and 2. So just write 1, 2. Is this clear? And second element is connected between the nodes 2 and 3. 2 and 3. Is this clear? Okay, just write the connectivity of the elements, that's all. So once you write this, next move on to element stiffness matrix. Okay, so here we have derived this element stiffness matrix in our previous lecture video of an one-dimensional bar element. Am I right? So after deriving, we have got the equation K is equals to AE by LE 1 minus 1 minus 1 1. So here we have 2 elements. So you have to write the stiffness matrix for both the elements. So first we'll write for the element 1. Element 1, K1 is equals to A1 E1 by L1 into 1 minus 1 minus 1 1. So A1 is the area of element 1. Similarly, E1 is the Young's modulus of element 1 and L1 is the length of the element 1. Okay. So here overall area of whole bar is same. In some questions A1 will be different, A2 will be different. That time A1 and A2 you have to take into considerations. In this question area is same throughout the bar, so you need not worry, and even E is same throughout the bar. Okay, it's the same material, so you need not worry about that. Okay. So now K1 is equals to AE. Just substitute the values of A and E. It's given in the question. AE by L1. L1 is the length of the element 1. Length of the element 1 is 500 mm. Just substitute everything in mm. 1 minus 1 minus 1 1. Just keep 500 cancels and this keep as it is common. Is this clear? Okay. Write that as equation 1. Next go to element 2. Element 2 K2 is equals to A2 E2 by L2. Similarly like this. A1 E1 by L1, here A2 E2 by L2 into 1 minus 1 minus 1 1. AE both are same in both the equations. Substitute the values, cancel it, write this, you will get one more stiffness matrix. Okay. So here your basics comes into the picture. When we were discussing in the module 1, I have said you the steps in FEM. Okay. So there in the third step we have said element stiffness matrix. So this is the element stiffness matrix. Once the element stiffness matrix is done, you have to assemble the element equations to form the global stiffness matrix. Okay. So you have to assemble this element stiffness matrix, these 2 elements. This is just one stiffness matrix of the first element, this element, first element. Similarly, this is stiffness matrix of the second element. Now you have to form a connectivity between these 2 elements, right? So you have to form the global stiffness matrix. Okay. In order to form the global stiffness matrix, before going on to that, you have to number this element stiffness matrix for your understanding. Like that's why we have written this element connectivity table. Okay. So once you have got this matrix, so the first element is between the nodes 1 and 2. Correct. So just write 1 2 1 2 for your understanding. That's all. Okay. And the second element is between the nodes 2 and 3. Correct. So just for the K2 you write 2 3 2 3. Is that clear? First element 1 and 2, second element 2 and 3. First K1 1 2 1 2, second K2 2 3 2 3. Is this clear? Next, global stiffness matrix. Global stiffness matrix K is equals to K1 plus K2, that is this plus this. Okay, so K is equals to, see, what will be the size of the global stiffness matrix? The size of the global stiffness matrix will be the maximum number of nodes in this element. Okay, so it is 3. So the size of the global stiffness matrix will be 3 cross 3. Is this clear? Okay, the size of the global stiffness matrix will be 3 cross 3. So, or you can see here itself, it is 1 2 2 3. So obviously the size will be up to 3. So just to take this as common, and both the things it is common in K1 and K2. So just I have taken that as common, and then draw a matrix of 3 cross 3 and number this 1 2 3 1 2 3. First number this outer thing. Okay, then write the coordinates of this 1 1 2 1 1 1 2 1. Similarly 1 2 2 2 1 2 2 2. Getting it? Write the coordinates, or in simple way, just write this first matrix in this first block. In this first block. Is this clear? Okay. And write the second matrix K2. K2 starts from 2 2. Is that right? Please understand this. K2 starts from 2 2. Coordinates 2 and 2. So here it is. Where is 2? 2 is here and 2 is here. So it starts from here. So earlier in the K1 matrix I had 1. So 1 plus 1 here. Understood? And it starts from here. Write the second matrix K2 here. Okay, so this part is added. Is this clear? Okay, and the other blocks write it as 0. And the other blocks write it as 0. Okay, so just add this, you will get it as 2. Okay, is equals to now 10 to the power 3. The whole matrix becomes 1 minus 1 0 minus 1 2 minus 1 0 minus 1 1. Okay, next, finite element equations. We have got the global stiffness matrix. Next is the finite element equation. Just we are following the steps in finite element method. So KQ is equals to F is the finite element equation. What is the K equation or the global stiffness matrix we have got is this equation. So write the K equation here, K matrix here. Okay, and Q. What is the Q matrix? How many Qs we have? Q1, Q2 and Q3. So just write Q1, Q2, Q3. Okay, is equals to F. And what is F? F1, F2, F3. So Q1 is 0, Q2 and Q3 we have to find out. F1 is R1, F2 is 0 and F3 is minus 12. Where did I get all these values? I've got all these values from here when I write the boundary conditions. Okay, so just be careful there. Next, by using elimination method. So in the elimination method, wherever you have 0 in the Q term, wherever you have 0 in the Q term, strike out that row and that column. For example, 0 I have here in the first row. So I am striking out the first row and the first column of the K matrix. Is that right? Okay, understood? So after that, I am left out with this part, this and this. Okay, so I'll just write the equation. So 207 and 10 power 3 is equals to, just multiply the matrix, first row and the first column is equals to this. Okay, so 2 into Q2 plus minus 1 into Q3 is equals to 0. Okay, I repeat, 207 and 10 power 3 is common. 2 into Q2 plus minus 1 into Q3, row into column, is equals to 0. Similarly, 207 into 10 power 3 minus 1 into Q2, minus 1 into Q2 plus 1 into Q3 is equals to minus 12 into 10 power 3. Okay. So just solve these two equations in your calculators. You will get, in your calculator, you will get Q2 and Q3. Q2 is equals to minus 0.05 mm and Q3 is minus 0.115 mm. Is the nodal displacement. So these two are the nodal displacement at nodes 2 and 3. So this question mark we have found out. Is that right? So what else he has asked in the question? First is the nodal displacement we have found out. Next is the stresses. So how to find the stresses? In order to find the stresses, we have the formula. In order to find the stresses, we have the formula. Sigma is equals to E by L minus 1 Q1 and Q2. Q1 and Q2 because element, we are doing it for the element 1. See from the element connectivity table, see sigma 1 is equals to E1 by L1 minus 1 Q1 Q2. Why Q1 Q2? Because the connectivity of the element 1 is between the nodes 1 and 2. That is Q1 and Q2. Similarly, if you want to find the stresses of the node 2, it is Q2 and Q3. Okay, is that right? Is it clear? Okay, so just substitute the values. You know the value of E, you know the value of L, minus 1, Q1 is 0, Q1 is 0, and Q2 we have found out, Q2 also we have found out. So substitute the values, multiply this and this, minus 1 into 0, and 1 plus 1 into minus 0.05. Just to simplify this, you'll get sigma 1 is equals to minus 20 into minus 20.7 Newton per mm square. Okay. Similarly, go for element 2. Sigma 2 is equals to E2 by L2 minus 1. Element 2 is between the nodes 2 and 3. So it is Q2 and Q3. So sigma 2 is equals to 207 into 10 power 3 by 500 minus 1 Q2 Q3. So sigma 2 is equals to minus 26.91 Newton per mm square. Okay. So very simple problem and very important problems. All the bar problems are very important. So just be careful and go through the problem. Okay. We'll move on to the next problem. So we'll move on to the next problem. So the second problem. For the bar loaded as shown, find nodal displacement, support reaction, element stresses. So in the earlier problem, he has asked only nodal displacement and stresses. Now one more thing is the reactions. So three things we have to find out. So it is a stepped bar fixed at both the ends and the load is applied at the middle. P is equals to 200 kilonewton is the load applied at the middle, and at one the first length of the bar is 300 mm and the second length of the bar is 400 mm. And here he has given the material also. Material is also different of both the sections. The first section material is aluminium, where area of that first section is equals to 2400 mm square. E is equals to 70 to 10 power 9 Newton per meter square, so it is 70 to 10 power 3 Newton per mm square. Similarly, second one is steel, area of 600 mm square, E is 200 into 10 power 9 Newton per meter square, that is equals to 200 into 10 power 3 Newton per mm square. Okay. So once all this data is given, the next step is writing the finite element model, FE model. So this is FE model. So finite element model. So just write the line diagram. 1, 2 and 3 nodes is required here, because one at fixed end I need a node. Wherever there is a change in the cross section I need a node. Wherever there is a fixed end I need a node again. Okay. And which are the nodes fixed? The node 1 is fixed and node 3 is also fixed. Okay. And P load of around 200 kilonewton is applied at node 2. Just number it 1, 2, 3 and elements 1 and 2. Okay. Next, write the displacement and the forces. Displacements Q1, Q2, Q3, forces F1, F2 and F3. Q1, it is fixed, right? So wherever it is fixed, displacement is 0. Even here Q3 it is fixed, so displacement Q3 is equals to 0. Q2 is not fixed, so Q2 you have to find out. Okay. Similarly, F1 is fixed, so wherever there is a fixed, when the force is applied, there will be a reaction force here. Okay, so F1 is equals to R1. Okay, there is a reaction force. F2, the force of 200 kilonewton is applied here, so 200 into 10 power 3 Newton is applied at F2. And F3, it is fixed, so there will be a reaction force R3. Okay, or in simple understanding, wherever the displacement is 0, just write R there. Okay, so that you will not make any mistake in the exam. It is just one more method of cross-checking it. Okay, this is clear. If you write this step properly, then this other steps is very simple and easy to understand. So make sure, if you have any doubt, please go through it and ask me. Next, element connectivity table. Element, this is E element, and this is nodes. Okay, we have two elements, element 1 and element 2. Element 1 is between the nodes 1 and 2. Element 1 is between the nodes 1 and 2. Element 2 is between the nodes 2 and 3. Element 2 is between the nodes 2 and 3. Similar to the previous problem, how we have solved. Okay, next, element stiffness matrix for bar. We have derived this. K is equals to AE by LE. 1 minus 1. Minus 1 is the element stiffness matrix for the bar, which we have derived in the previous class. Next, for element 1, K1 is equals to A1 E1 by L1. Okay, A1 E1 by L1 into 1 minus 1 minus 1 1. So you have to be very careful. This is the first element. Okay, so A1 E1 is this one, and L1 is 300. Okay, so A1 E1 by L1. Is this clear? So just simplify this. You will get 560 into 10 power 3. Keep 10 power 3 as common and take 560 inside the matrix. Multiply it inside the matrix. So it is 560 minus 560. 560 into 1 is 560. 560 into minus 1 is minus 560. 560 into minus 1 is minus 560. 560 into plus 1 is 560. Okay. So this is K1. Okay. Next, for element 2, K2 is equals to A2 E2 by L2. Okay, so A2 E2 by L2 is 400. So just be very careful and then simplify this. Take 10 power 3 as common and take rest all the other things inside the matrix. Okay, so you found out K1 and K2. Next is global stiffness matrix. So here, before writing the global stiffness matrix, just go through this element connectivity. The first element is between the nodes 1 and 2. So K1 is, just number it 1, 2, 1, 2. Second element is between the nodes 2 and 3. So second element 2, 3, 2, 3. Is this clear? Next, K is equals to K1 plus K2. Okay, so K is equals to 10 power 3. I've taken common in both K1 and K2, so 10 power 3 I'm taking it as common, and write this matrix's coordinates. So 1, 1, it starts from 1, 1. Okay, so just write this matrix, first matrix here. Similarly, second matrix starts from 2 and 2. Where is 2, 2 and 2? You can see here I've summed up here. So this part is getting added. Okay, very simple matrix addition. Just be careful, please don't make any mistakes here. Next is element stiffness, finite element equation. KQ is equals to FK, we have got it. So just write that K, Q is Q1, Q2, Q3. Q1 is 0, Q2 we have to find out, Q3 is 0. So 0, Q2, 0. Next F1, F2, F3. F1 is R1, F2 is 200 in 10 power 3, F3 is R2. Wherever you have 0, it is R there. That is, there will be a reaction force which we have to find out. Okay. Next, using elimination method. So using elimination method, so I have said you, wherever there is a 0, strike out that row and that column. For example, here 0 is in the first row, so strike out the first row and the first column. Similarly, 0 is in the third row, strike out the third row and the third column. Is that right? So only one term is left out, only that middle term is the left out, or only we have to find out Q2, right? So 10 power 3 into matrix multiplication, this into this, 860 into Q2 is equals to 200 into 10 power 3. Simplify this, you will get Q2 is equals to 0.2325 mm. That is the displacement. So we have found the nodal displacement. Next is the support reactions. So reactions, what are the reactions is the R1 and R3 we have to find out. Okay. In order to find out this reactions, the same matrix, wherever R is there, you multiply that matrix term. Okay. So 10 power 3 into 560 into 0 plus minus 560 into Q2 value we know it. Okay. Similarly, 0 into 0 is equals to R1. Okay, you will get R1. Similarly, 10 power 3 into, where is R3? This row, correct? So 10 power 3 into 0 0, 0. Minus 300 into Q2, minus 300 into Q2. Next 300 into 0, 300 into 0 is equals to R3. You've got one more equation. So R3 is equals to minus 69.75 into 10 power 3 Newton. Clear with finding R1 and R3? So we have found nodal displacement, support, reactions. Next is stresses. Stresses, you know it, already we have seen in the previous equation. So sigma 1 is equals to E1 by L1 minus 1, 1. We are finding the first element. So it is between the nodes 1 and 2. That is Q1 and Q2. Okay. So E1 by L1 minus 1, 1 minus 1, 1. Write the values of Q1 and Q2. Multiply this and this. You will get this value. Just simplify this. You will get sigma 1 is equals to 54.25 Newton per mm square. Similarly, sigma 2 E2 by L2 minus 1, 1. Element 2 is between the nodes 2 and 3. So Q2, Q3. Okay, just multiply this and this. Minus 1 into 0. Minus 1 into 0.